How's the conference so far? Enjoying it? Nice. How many of you have read the book Kotlin in Action? That's the author? How many of you are watching YouTube videos? Release videos? Okay, I have more groupies. Thank you very much. So I'm Anton, this is Svetlana. We are from Kotlin team, the developer advocates, and we are going to talk about KotlinX libraries today. Let's go on the next slide.
Let's start.
Right, so what is KotlinX? X stands for extensions. This is a set of libraries developed by the Kotlin team. They are all multi-platform. And, well, these are kind of the core libraries that are not obligatory. They're optional. If you go to the GitHub account of Kotlin, click, you find a list of those projects. Those are not only the libraries that are also useful tools like cover, lint check, and benchmark repository, but, well, most of them are libraries that you can just include in your project. Some of them are configured as compiler plugins. And as you can see, 2 of them are already stable, like Coroutines and serialization, stable libraries, and the others are either in alpha or beta status. So today, we're gonna explore a few of them, a few exciting cases, highlight some of the APIs in those libraries that we feel is interesting in the context of a demo application.
Yep. So we wrote a sample demo application, which is a multi-platform simple chat app. And it uses obviously KotlinX libraries. And in this talk, we're going to look through and discuss our libraries from the perspective how we are using, how they help us to write our demo app. And to start, let's look how it works. Let's see how this app works. And so that for us it was easier to
explain the context.
Yeah, to explain the thing. So this is our desktop client. So we have it available as desktop. We use Compose multi-platform, and it provides us different clients. So we share the client code. So we have desktop. We can connect to it from desktop. This is iOS. We can join the chat. And this is Android. And we also join the chat. And we say, like, hi, Kotlin conf, and which is important for our discussion of the libraries. When someone is typing,
pay attention to the other windows in the chat, like between the messages section and the text area, there is like a little text appearing. Maybe you can zoom in. No? Try zooming in.
A second. Zoom in. Nope.
No? Let me try that for you.
Yes. But
OK, it doesn't zoom in this setting.
But you can see that there is this appears that someone is typing, and this is important for our future discussion. So we can type the message, and when we're typing, we see that desktop is typing. So this is our basic app. Here you see Hadi is typing. So how it is implemented? On clients, we use Compose multi-platform. We use Cater for networking, and the set of KotlinX libraries that we're going to discuss today. On server, we use Cater and the same set. Compose multi-platform, if you're interested, explore the implementation. This sample app will be available for you to dig in and to see how it works. It's not focus of our talk today. We just use this because it's great, it works, but we are going to focus on the libraries. Again, with Cater, we're using Cater server, but today our main focus is this KotlinX libraries, and we'll see the use cases that we see for them in this implementation. So our libraries in focus for today: serialization, coroutine, datetime, immutable collections, and cover. I suppose that probably not everyone is aware of all of these libraries, and some of them are still in alpha state, so we hope you'll find something useful here.
Right, so we start with serialization. So basically to set some expectations for how the demo and the whole presentation is going to flow, we're going to have a few sections on each library and then, highlight some of the use cases for each library separately. So serialization, how many of you are using it? Perfect, everybody knows it. Everybody knows why serialization is needed. We're going to convert some classes into some format and back. If the clicker works, I can proceed further. Basically, to use it, you configure it in your build script as two artifacts. You have to configure the plugin and a dependency. And that is because you actually have a compiler plugin to generate the visitor code to get rid of the reflection so that the runtime library can use this code and, serialize and deserialize objects without reflection. And then it also provides you the APIs to work with this library, to work with the code, to call this serialization API from your application. In our application, we have a very simplistic type hierarchy implemented. So all the chat events that you have seen in the demo, when you are sending something, there is a message event that delivers a text message into other chats, other clients. And then there is a typing event. When someone is typing, there is indication in other clients that someone is typing. So how do we serialize that? Let's start with the baby steps. We're gonna just serialize one event, assume that we only have message events, so everybody just receives text messages. And, well, for real situation, we are using the interface as well. We're going to mark the data class as serializable, and we're going to just use it in our code. Create an instance, encode it as a string, decode back, everything works. Perfect. So what if we proceed further? We introduce another event. Should work, right? Everything is marked with serializable. Everything is good. And we run this code. We create a list of messages. Automatically, the type inference kicks in and says that there is a common supertype that the list has, like the chat event, right? Not a message event. It's not a list of message events. It's not a list of type events. It's a list of chat events. And in the loop, let's encode and decode this and run the application, and boom, it crashes. Why? Because the exception will tell you that this class is not registered for polymorphic serialization. What's wrong with this? Well, we can just mark our, so why doesn't it work in first place? So assume that we have a chat event that as a typing event, and we want to encode it as a string. It looks like this, right? We just assume that there is one value in this data class. What if we introduce another data class that has the same shape? It only has one value of the same type. Basically, they serialize to the same format, right? The same string. What if we want to deserialize it, again, decode it back to the object? So the shape is the same. We want to encode it back to some type in our Kotlin application. How does the application know? How does the library know which type should it be? Typing event or user-joined event? We have to be explicit about that. The message needs to contain a special key to indicate which type it should be. So the library knows exactly which type should it produce when it encodes the string. So we have to be explicit. That's the philosophy behind the design of serialization library. So for our solution, it's pretty easy. We just mark the hierarchy as sealed. It means that the hierarchy is closed. It's explicit to the library. And library can scan the shape of the hierarchy, cannot change. It's predictable. So in this way, it's explicit. Right, and we mark it as serializable as well, of course. So for the open hierarchies, in case you don't have control over the code, you cannot mark the supertype as sealed. You cannot seal the hierarchy. It's called open hierarchy, and for this, you can use the APIs in the serialization library to register them for this kind of use case. We are not going to cover it like in our demo today, but it's just a possibility. All right. So what is Kotlin serialization? It's a multi-platform, and it's a stable library. So if you have a case where you have to develop an application for multiple platforms, and you need serialization, most likely you do, that's the library you want to use. It doesn't use reflection, means that it actually gets rid of some performance overhead as well, and it works as a compiler plugin because of that. So it is aware of Kotlin specifics. So in Kotlin, we have some syntax that is very specific one, like named arguments, default values. So the library can handle that as well. And it supports polymorphism, like specifically in our demo, it's an interesting case. If we implemented it in a naive way, we would get an exception in runtime. I wish one day it would be a compile time exception, but maybe. She's not happy. All right. And we proceed to the next library. You want to talk about this?
Probably.
You should.
Yeah. So we are going to now talk about coroutines, and coroutines is a huge topic. It takes several hours to cover it properly, and that's why we are not going to explain you the basics of coroutines or suspend mechanism or whatever. But we found that we have a very interesting use case to highlight some differences for their way how we use coroutines in our chat app. So we are only talking about how we use coroutines as specifically flows in our chat application. And generally, we need to do simple stuff. We need to send and receive events from clients and do the same at server. At server, we need to broadcast the events to all the clients. And we found out a very interesting use case in our app, because we use different types of flows in our application. Who are using flows or knows the concepts? Okay, so most of you are already aware. So flow is analogous to reactive stream in some other libraries. It's like it's different from just a collection, a list of elements, because it also gives you the perspective of time. So it's like an element elements coming us in different periods of time. And in our case, we are using shared flow on server, and on client, we divide it into UI layer and network layer. We keep it simple. Also, it's like it's best for samples to be as simple as possible, but still cover the use cases. On client, on network layer, we use the basic flow off function, which is called flow, and we also use state flow on UI layer. And now we're going to discuss that in detail, all these use cases. So let's start small. Let's start with the logic that sends the event from client. So we are going to send it somewhere from the UI layer. Like here, we have our chat app, and the user types the message and clicks on the send button. And at this point, we use compose. So this handler, what happens on the button click, it just calls a method from the view model. Interesting thing to notice, yeah, with compose multi-platform, we share also view models in our demo application. So here, we click on the send button, and we can send event from chat server. So we call a method from our network layer to simply send this event. I think that currently it's very much straightforward. We send our message event with user, with message, and with the current time. And our network layer, when it sends the event, it just provides us the way to send the event. It's simply calls the socket and sets the event through the socket. We use WebSockets in our implementation, so our server is communicating with all the clients via WebSockets. It's a modern way to perform such real-life communication. So whenever a new client joins, we establish the new WebSocket connection with them, and all our messages, our events are going through WebSockets between server and client. So it's also an interesting, simple case of applications of WebSockets. And with Cater, it's pretty much straightforward. So it's like you just say socket send serialized. That's it. And when we start on the client UI layer, we launch Coroutines in the chat servers that invokes this code that sends the client, the event. OK, so we sent event from the client. It was pretty straightforward. So we just say, OK, socket, send our event. And now it comes to the server, and interesting thing begins, because we need to broadcast this event to everyone, to all the clients. And for that, we decided to use shared flow, mostly to demonstrate you the abilities of shared flow. Our chat is a bit constrained because it doesn't preserves us the history of the events, the whole history. We don't store it, so it's more like real-time chat app. It's like we want to hide our messages history just in case everyone is interested in it. We don't want to store it, and we decided to use this technology. And of course, it's also to demonstrate you the power of shared flow. So what is going on server? Server receives the events and broadcasts, resends them to clients. We also use the server as single source of truth for events, so client sends the events, and then it receives it back from the client, and then it chooses, again, for simplicity, just not to have any more complications. So how it is implemented in the server? We configure, it's like when we configure sockets, it's like Cater code, it's not that important, but we can use our, like we say, application, configure sockets, and then we install routing, and on each WebSocket connection, we call handle socket. This is our own function that we are going to implement right now. And we define mutable shared flow of chat events that is going to be shared between all our WebSocket connections. So whenever a new client joins, whenever a new client connects our server via WebSocket and establishes new connection, the Cater server calls this handle socket function. So it's like for every socket, we start this new handling mechanism. Again, I want to highlight that in our case, it's very much simplistic. So we use mutable shared flow as a single source of truth for all our events. And also for simplicity, in the slides, we use it directly. In the chat implementation available at GitHub, it's a bit more, we have it inside an abstraction, but we decide that in our case, in the slides, it's simpler for understanding if we have it directly. But if you decide to browse it later, you'll see that it's actually hidden behind the abstraction. And we don't, as I've told you, we don't store all the history of the events. So let's implement our handle socket function. And we need to do two things. First, we receive events from client, and then we need to send all events to client. And when we're talking about receiving events, we only receive events from this specific client. So it's like whenever this client sends us message or typing event, we receive it via WebSocket. But we need to send all the available events from all the clients to this specific client. So it's like messages from everyone are sent via this WebSocket through this WebSocket from server to all the clients. First part, receiving elements from client. Again, pretty much straightforward. We can call socket receive deserialized, and then we need to somehow handle the event. So what is it? This handle event, we need to share this. We need to notify our single source of truth that this new event came. And because we use shared flow, mutable shared flow, we simply need to emit this incoming event to this shared flow. So what we do here, we simply say event flow, emit event. And that's it. So we notify our mutable shared flow that, hey, someone has written something or someone is typing. So we implemented the first part. Let's talk about the second one. When we need to send all the events to client back, we need to do something like this. We need to also launch new coroutine that says for all the events, we need to send this event to client, right? So we need the same socket, we use the same socket, and we send all the events to the socket. And what is this for all events? Again, we access our single source of truth, our mutable shared flow, and we need to subscribe to all our events. And how we do it? We say event flow, collect all the events, and for each event, we sending it to our client. That's it. This is simple implementation using shared flow to broadcast event to clients. And from our perspective, this example demonstrates you what shared flow is about, what it is, and the use case of receiving and broadcasting events to all the subscribers. We also can configure the replay parameter, which makes our chat app a bit more, which improves our chat app, because if we configure this replay, our mutable shared flow is able to store this specific number of events, and then when new client joins, they don't see the empty page, but they see this replay number of parameters. If we don't specify replay here, when the new client joins, they will only see new events that will later come, but they will see empty screen, and whenever something new comes, they will see it. But if we specify replay, they will first see this specific number of events in the application. Again, just to highlight, in real life, you probably need a different persistent solution if you want to store the whole set of messages, but of our sample app as an illustration of what shared flow is capable of, that works great. So we're done with server part. Now we are coming back to client, to network layer, and let's discuss how we use flows there. And in the network layer, we use flow of chat event, this function that creates you a new flow of event. And this is so-called cold flow. That means that until you start collecting the values, nothing happens. So in comparison with our mutable shared flow, which exists independently on us, independently on subscribers, when we defined it, it already started to be able to receive and produce the events. This cold flow does nothing until you start actively collecting the events. And why do we need it? Mostly when you create some service APIs, provide API to access and to observe, to subscribe to some flow of data, in our case, flow of chat events, you can, in your network layer, define this function and then use it from your consumer. So here in our UI layer, we say collect, and we start collecting the events. And now we have another flow, state flow. And this one is used in our UI layer, in our view model, to represent the state of our app. And as a state, we also want to show not only the latest message, but the whole history of messages, the whole list of messages that we have. And here we need to store all of them in a list. So how it works, whenever the new message comes, a new event comes, it comes through the WebSocket, it goes to network layer, and then through API, we collect it and add it to our state flow that stores the list of messages. So here, new event comes, and each new event we add to this list of messages. State flow is used to represent the state. And in this case, it's like live state, analogous would be live data, something that represents the state that can change and that can be updated. And in this case, we collect our events from the WebSocket, and on each event, we check if it's message event, we need to add this message event to our message flow list. Here, we're adding the new message so that each client stores all the messages that it received. And it shows to the user the whole list of messages, not just the latest message. You see this pattern. It's also very commonly used when we defined our message flow as a private mutable state flow of a list of messages and expose it to the compose code from the class as a read-only state flow. And as Roman shared with us in the keynote, later in Kotlin 2. Something, we'll have a better syntax for it, probably something like this, probably something else. But the thing is, we will not need these two variables, but currently it's a very typical pattern that you see all over the places when you have just two variables, one private one, and the other one is a public one exposing a different read-only type. So we're done with our discussion with flows. If you're interested, please browse the code to better see in action how this all works, how it all functions for you. So you can also experiment with replay functionality. You can specify it as 0 and see that, yes, you only see the latest messages. You can specify something, and then you see that all the messages are replayed for you. And as a conclusion, I want to highlight that this flow as a part of verb is called, so-called cold flow. Nothing happens until you start to use it, until you start to collect it. And shared flow and state flow are hot flows, which means that whenever you created them, they already start their existence, and they don't depend on whether there are some consumers, subscribers or not. Short summary, cold flow, part of your service API, the consumer decides how to use it. State flow, for represent changing state. Shared flow, flow of events can broadcast to all the subscribers. And shared flow is probably the least used one, but still it's important. It might be useful to understand how it all works. In typical applications, you will only meet the first two, like flow of and state flow. So that was all with Coroutines and our next library.
Yes, and right after that, we actually have a fun trivia about flows as well, right? Did we include the puzzler? Yes. So just a small sidekick into datetime library. That's also a multi-platform library, by the way, but let's look into the chat app first. So in the chats, you usually indicate when the message was delivered, right? Some kind of a timestamp. And to implement that, we used our KotlinX datetime library. It's under the development. It's an alpha. Well, you don't need a plugin for that, so you just configure a dependency. And it provides you a few main types that you work with. For those of you who come with Java background, it reminds those types, remind you of Java datetime types, but they don't match one-to-one. In Java datetime, you have slightly more. So to represent the date and time information, you have local date time, local date, and local time, and also the time zone to indicate the time zone. And then you have instant to represent a moment in time, and the clock as a source of those instants. So imagine we have an event, a message event comes in, and we want to represent the timestamp as local date time. Is anything wrong with this, Sveta?
I don't know.
Think about this.
Probably. It's all good. But if Anton asks us?
No? Okay.
Okay, something.
So I live in Tallinn. Sveta lives in Munich. And I suddenly get a message, or you suddenly get a message from the future. It's nice to be Marty McFly sometimes, but it's not probably what you intended to do. So time zones are hard, and to fix this, it's better to use a moment in time and actually render this information in the presentation layer according to, time zone which you are in. So we could fix it like this. If we proceed further, on the next slide, you can represent this time. If you can format it in a different way, and the API actually provides you a few shortcuts for this. So, for instance, if I want to format my timestamp as a date, I can get this date information, and just check if this date is actually today. So, if those for the older messages, I would put the date information in, but for the messages I received today, I don't have to do that. I can just render time. And for this, we have a very handy function in the clock system class. That's probably an extension function, I think. So you can get today, from the APIs and compare with the date and then decide. So another interesting case that we have in the application is grouping the messages by time intervals. So imagine you have all those individual messages in the chat, and you render them one by one. But if a message comes from the same person who texted it, so he just texted it a few seconds ago, you probably could merge them and append them together by some condition, if it comes from the same user. And that condition could be if the message was sent with a time interval less than some period of time, let's say 10 seconds. So I appended the message, and it looks like 1, right? So how could you do that? In this example here, group consecutive by is not a standard library function. That is custom function. If you download the sources for this demo, we'll have links in the slides. You will see that it's just a small implementation that implements this grouping. But what we want to highlight here is that the API provides you some overloads and some extensions in the library that enables this very fluent, understandable, non-verbose, type-safe syntax to express the condition. Second timestamp minus first timestamp, we subtract 2 instants in our applications and then compare to the duration. We can do operations here. Right, so that's an experimental library. Don't use local date time to represent a moment in time. Use instant instead. And there is some information on the slide that I won't dive into right now. This is for you to browse later. So we could proceed and save time for the interesting stuff.
Our next topic is probably the listener library, and which is also still an alpha, still experimental. So it's KotlinX collection Immutable library. If you want to use it, you need to include this dependency. It's work in progress, so it's like 0 version. And what I want to highlight here is that when you use list, when you see list in Kotlin as a part of your API, you should be very aware that it doesn't depend that this list is immutable. It is read-only, which means that you only have read-only access to it, but there is no guarantee that it's not a mutable list under the hood. And there might be a really tricky bug with this. So it's like if you write the code like this for any view model, and we decide to kind of save memory and it's like say, okay, let's use the same mutable list to store all our messages, and we'll return this same mutable list over and over again to our client to compose code. It doesn't work we only see we don't see any messages at all. It's like you write this code, you run it, you can try it. I mean, like you can change it in our demo app and make sure that it really works like this. So it's like, and I think that it's a useful piece of information just to understand and to avoid it in general. You see that it's the same initial mutable. It works because it's the same initial mutable list and nothing changes. So it's like you don't see any messages. And here there is the same puzzler, but without any compose code, without any dependencies. Let's just print the output. And if we run the code, it's like here we create a mutable list and we decide to emit the same list to mutable state flow, and we update the content of this mutable list. And then we print it and we see empty output, and that's it. We don't see any new messages, but here should be 1, 2, and so on. Why does it work? Because at first, when we only start this code, we emit this list to our state flow, and state flow is designed to only update it when the state actually changes. So when it compares the elements, and when the state changes, it says, okay, there is new state. So here we emit this list, it refers to our list in memory, to our mutable list, and we print the result is printed. Then we emit the next list. We add the element to our mutable list in memory, and we emit this new list. And now stateflow says, okay, let's compare these two elements, these two lists. It compares them, but they are the same reference to the same object. So equals on them returns you true. And stateflow does nothing, because it says, okay, it's the same element, so no need to emit anything. And you only see as a result only the first message. So it's kind of tricky. You might have spent some time on figuring out why your app doesn't work, because you somehow decided to use mutable list instead of returning you the new data structure each time. And the fix is easy. You just return uList when it has changed, right? So it doesn't use any mutable list so far. You only say that, okay, I update the previous list and return uList when new message comes. And then stateflow works correctly and returns and understands that, okay, new element comes with new content. And an alternative is to use truly immutable collections, like to save yourself from this problem, and you can use these immutable libraries. I wouldn't say it would be enough justification for now, because they are still in alpha, they are still a work in progress. So I want to add more to the story. Before this, let's reiterate the benefits of using immutable collections. And in general, it's like when we're talking about truly immutable collections, it's like it's safe to use them. It's safe to use them in concurrent applications. It's safe to use them to share them between threads, between different coroutines, no risk into running into race conditions. And they are more memory efficient when you really need intermediate updates. Like in our case, probably we're not that. It's not that important, but still, it would be a bit better. However, there is more to the story. And let's talk about composables for a bit. Sorry for those of you who are not really aware. So this part probably assumes the only part that assumes your kind of knowledge, a bit of knowledge of compose. And compose can skip recomposition if the state hasn't changed. So even for those who doesn't know anything about it, probably you've heard it. It's like the power of compose is that it optimizes lots of things for you, and it hides, it doesn't do unnecessary work, so if the change hasn't changed, it does nothing. In our case, let's look at this example of state change. We have chat with a couple of messages, and we see that typing users so far is empty. But now someone started typing, and the state changes. So it's like we see that Anton is typing. The question, should we recompose their list of messages that has not changed? So should the compose keep the recomposition of this messages view? And in our case, you can browse the code. We have simple composables. So it's like, in our case, the whole composable is chat screen, and it consists of 3 parts. First goes message list, then there is typing users, and create message part. So the question is, if our message list has not changed, will the corresponding message list composable be recomposed or not? And here, I'm not sure we have...
We don't have time for
I
this
think
anymore.
unfortunately, we don't have time for...
Believe us, or you can play with it
for the demo.
in the demo as well.
Yeah, you can play with it with the demo. We have this commented line that shows you, that just prints you the output for this message list. It's like if you use this message list composable, the first line is like prints, I'm recomposing it, and you can uncomment it and start it with this list, with using regular lists. And you'll see that if we use regular list, which is regular Kotlin, like list from the library, the compose will recompose this message list. So the compose will recall it, will call this function, even if messages hasn't changed, even if this message list hasn't changed, right? So when we have these new events from the user, it will still recompose the messages. But we would expect it won't, but it is still, if it's just regular list, it still recomposes. However, if we're using immutable list from this KotlinX immutable collections library, then compose will understand correctly that, I can skip this recomposition. I can skip it because my messages hasn't changed. And it turns out that compose acknowledges immutable types from KotlinX collections immutable library, and it only does this recomposition for types, for immutable types or for stable types that are not changing. I'll give you the link a little bit later about this internal. So it's a kind of complicated topic, and if you're interested, dig deeper into this. But the whole idea is that it turns out that to avoid some extra work for compose, you will benefit from using KotlinX immutable libraries. And in our case, we use immutable list now as a part of our API, and it all works. We use a different interface, persistent list, for modifications. You can also browse the code and see that we need extra interface. It's like in KotlinX, we have this separation, immutable, persistent, and persistent interfaces are used when we need to apply any modifications. For this, it just extends the immutable list. And when we need to update it, we need to store it as a persistent list, and when we expose it to the client, we expose it as an immutable list. So here, when we update, we use persistent list. A brief summary for immutable collections library. It's multi-platform. It's like as we all these libraries are multi-platform. It's currently in alpha. More operations to be supported before its stabilizations, and it provides interfaces for truly immutable collections. And you need to use persistent collections for modifications. And this is an article that I wanted to show you about, explaining about how exactly Compose is doing this recomposition. And Compose can skip recomposition with immutable parameters. It acknowledges immutable types from this library. And you can see it in action with this sample chat app. You can replace immutable list with list, start it, and see that, yeah, it actually works. Not lost. And I think that now we are, because we are checking time, so we are discussed our different libraries, and here is the links. You also find them in the presentation later, where this chat app is stored. You can play with it. You can see all these libraries in action, and observe all the effects that we just discussed, play with it, play with flows, see that really immutable collections, using immutable collections impacts recomposition, and so on.
That's our message for you. If you need to use multi-platform libraries, you know what to choose. And with that, we are done for today. So thank you for coming. I hope you learned something new. And don't forget to vote for the talk.
Thank you.
Thank you.